How do databases ensure durability in the event of crashes? This is an important problem with any source that we use to store data, because once we have to persist the data in a disk storage, or any persisted storage, it has to be durable, right? So in this video we are going to discuss how a database, specifically RDBMS, ensure the durability of your data when it say that it has confirmed transaction commit, right? So we will look into the details, what happens under the hood when you perform a query and when it returns that the query has been successful. So let's have a detailed look on the processes that's happening behind the scene. So transaction, I hope all of you are familiar with this particular term called transaction. So a transaction means it's like wrapping a lot of queries, multiple queries, in a single block that is executed as one single unit. So in layman terms, it's like either all those queries are saved or committed, or none of them are saved. So this ensures the data consistency and reliability, right? Let's say you have 100 update queries, between start transaction and commit. So either all these 100 rows are going to be performed, 100 queries are going to be performed, or none of them are going to be performed. So there is no state like only 50 rows were committed. So either you get the full commit after performing all those 100 update queries, or otherwise everything will be rolled back and none of them will be touched. So this is essential for to maintain the consistency of the data and the reliability of the data, right? So now let's look how a transaction is being performed in an RDBMS system. So in this particular video, I'll be mostly talking about the systems implemented with the Postgres, but other DBMS like MySQL, SQL Server, Oracle, all of them follow similar, techniques. So before we get into the details, you need to understand how these tables are stored in the disk. So Postgres stores these tables as data files on the disk. There can be multiple data files for a particular table depending on how large the table is. So usually a large table is split into segment files. Each segment file is of 1 GB in size. So let's say if you have 10 GB of data in a particular table, you might have 10 different segment files named from 0 to 9, right? So this is how the database stores your data, which is present in a table, right? And if you look at the segment here, you can see that the segment is again divided into pages. So when you perform a query, the database knows which segment file to look for. So you might think that the database will directly load the entire segment file, which is of 1 GB in size, into the memory, into the database buffer, and find the rows based on your query's where condition. But that is not efficient, because you have to load the 1 GB file into the memory. That's not really efficient. So again, a segment file contains smaller subsegments, or you can call it as pages. So a page is a portion in the data file that is 8 kilobytes in size. So you have multiple pages within a data file, like page 1, page 2, page 3, page 4, each having 8 KB size. So when you query for a particular row, select star from users where ID equals 15, then the database knows which page to look for. So the database then, fetches that particular page, loads into memory, that 8 KB page into the memory, and then it tries to find out the row from that particular page. So this is how the tables are stored in the disk, and these tables are accessed when you perform a query. So let's say we want to perform an update query. So update users set status equals inactive, where last activity at less than or equal to a particular date. So you want to set the status of all users whose last activity was at a particular date to inactive state. So when you perform this query, first you have to find the rows that satisfy the where condition, where last activity at less than or equal to this particular date. So Postgres wants to load all these rows into the memory so that they can perform the update function there. So it finds the pages, it loads all the pages into the memory, make edits to those particular records in the memory. So those pages are now marked as dirty, right? So you know what a dirty page means. A dirty page means it has been modified and now it is in a different state compared to its original form. That means that needs to be flushed into the disk. But here's the problem. It is very difficult to flush these pages back to the disk. It's an expensive operation. It might take some time depending on what the operation was. So this is not the best way to persist the data in the disk. And here is another problem. If Postgres wants to issue a transaction commit, then it needs to be, the data, whatever data that you have modified within the memory, that needs to go into the disk. Then only Postgres can tell you that the commit was successful. Otherwise, it's like Postgres is lying to you. Postgres never lies to you. Postgres say that the transaction has been committed, then you can trust the word. It is committed. That means no matter what happens after this point, you will get the data. Postgres never lies to you. So this is the problem, right? So if it has to give you the commit confirmation, the data has to go into the disk, and the Postgres has to get the confirmation from the operating system that the particular file was actually saved. Unless Postgres gets that, they won't be able to give you the transaction commit success message. That's why a write ahead log is used, or called the WAL, the WAL file. So according to the Wikipedia, write ahead logging is a family of techniques for providing atomicity and durability, two of those as properties in database systems. Yeah, so I hope you understood why this particular log is needed. We need a faster and durable mechanism to issue commit to the client who performed the update query. So write ahead log is a simple journal where Postgres makes entry about the changes that are being done to the records in the memory. So just take the previous example. You were updating 100 rows. Whenever you update a row in the memory, it actually inserts a record into the val file saying that, hey, I have modified this particular record. That goes into the drive, into the disk, the val file in the disk. So it's easier because the write is random and it's sequential. So you don't have to find the right page and modify that particular page. You can simply write into the val file. So it's really very faster compared to writing into the actual data file. So yeah, whenever you perform an update, you write directly into the val file. So for all those 100 update queries, you insert records into the val file. So now it's persisted, right? So the val file knows what are the changes that are done to these 100 rows, but the actual data file is unaware of those changes because it's still in its old state. It doesn't have the new information, the updated information, the updated rows. But that is fine. We can always modify that later, because now we have a single source of truth that says, so this is the modification that was done to these 100 rows by these queries. So anyway, we have a persistent record, you know, we have a persistent record, so that's fine. So let's see, we have a transaction that has two queries in it. The first query updates the balance of user ID 1 to 500, and the second query updates the balance of user ID 2 to 0. So like we said, either both of these queries should happen successfully, or otherwise none of the queries should happen. So there shouldn't be any state like only the first query was executed and second one was not executed. It shouldn't be like that. So what happens? So you start the transaction, that particular event is recorded in the val file, then the first query is performed. So then the database loads the particular row from the page file on the disk into the memory. It performs the change. It updates the row in the memory and marks that page as dirty, and also inserts this change into the val file. Then the next update query, the row is again fetched from the data file in the disk, performs the modification, marks as dirty, and then record that particular change into the val file. Then you perform the commit. The commit is also written into the val file, right? But you know that the changes, the rows have not been changed in the actual data file. So now we have two places where we have the latest data. One is in the memory, the buffer, and the changes in the val file. So what happens if someone tries to query, like select balance from balances where user ID equals 1, then you have to return 500. But if you look into the data file, if you try to fetch from the data file, you won't get 500. It's still the old value there. But if you have the page already in the memory, yes you have, and it's marked as dirty, so you can say that it's 500 because you have already performed the transaction, right? So the question was, we didn't write it to the data file. Is that a problem? No, we don't care. We don't care whether the data was immediately written into the data file, because like we said, val is going to be our single source of truth, the write ahead log, because that's anyway persisted in the disk. That means we have the record. And now there is another process in Postgres called the checkpointer process. It is the duty of the checkpointer process to read from the val file, the write ahead log file, and perform the actual changes to the data file. Why the data file needs to be modified? Because the queries read from the data file, not from the val file. So whenever you perform a query, Postgres loads the data file into the memory, not the val file, right? So either way, the data files needs to be changed depending on the val records. So this is done by the checkpoint process at regular intervals, which again you can configure from the Postgres configuration settings. So Postgres modified the records in the memory, just like we said. And of course, as soon as it's performed on the memory, it's immediately returned to the valve file. So the checkpointer says that, oh, that's great. I will prepare the data file based on the unchecked records in the valve file, in the write ahead log file. So as the checkpointer was doing that job, the system crashed. So what happens now? Now you lost those dirty pages which was in the memory. Like I said in the previous example, you had the modified records in the memory, but now you don't have it in the memory. So, and it's not written to the data file either. What's going to happen if someone tries to perform the query select star from users where user ID is equal to 1, because we had already updated the balance for the user ID 1. But unfortunately, if Postgres tried to read from the data file, you have the old data for the user 1, because that was not performed. I mean, that was not written into the data file, because the checkpoint was trying to do that, but at that time it crashed. What's going to happen here? When Postgres reads from the data file, it loads a page into the memory and it does a comparison with the valve file, the write ahead log. And if it finds that some of the changes were not performed according to the latest records in the valve file, so there are unchecked records in the valve file, that means the data that we currently loaded from the disk page file into the cache, I mean into the buffer, is older. We shouldn't let the user read from the memory at this point, because it's old. We had already said to the user that the transaction was successful, so the user is expecting the new data, not the old data. So what Postgres does is, it tries to redo all the changes in the memory, or replay all the changes in the memory based on what was written in the valve file. You remember, right? All these changes, all the records of these changes are now available on the valve file. So the Postgres just need to update the page in the buffer based on the valve file. That's it. So once that has been performed, that changes have been done on the buffer, on the page which is in the buffer, then Postgres can let the client read from the buffer. So why it is called a read or replay? Because you remember, right, we already had the changed data in the buffer, because we actually performed those changes on the memory itself. But unfortunately, due to system crash, we lost all those changes, and that wasn't added to the data file either. So we had to redo all these changes to the page based on the valve records. So again, at some point, the checkpointer will again go through the valve file, find out the unchecked records, performs the actual generation of the data file based on the valve records. So once the valve records have been added to the data file, it could simply be deleted. Valve file is not needed after that. So it's a checkpointer process. It's a very critical process in Postgres. It is the one that actually turns the journal entries in the valve file into the actual record file or the page file that Postgres can directly read into the memory and let the client read from the memory. So another question that you might have here is the val write reliable? Because val is the single source of truth, and it's the most critical file that we have in our database system. If the val file is not written, then we don't have the data anywhere. So what happens here? So Postgres, as soon as it makes a change in the memory, it wants to write that record into the val file. So anyway, the database sits on top of an operating system. It could be Windows or it could be Linux. It could be any other OS, right? So Postgres cannot directly write to the SSD or the disk. Postgres cannot directly write to the disk. It has to go through the operating system. So Postgres actually tells the operating system, hey, I have this val file that needs to be, stored in the disk. But then OS has this problem. OS doesn't always write the changed files into the disk immediately. OS again has its own cache. This is called the file system cache. So it actually keeps the modified files in the cache and waits for more writes to come, and only when the buffer fills, those particular caches are flushed into the actual disk. Because writing to disk is an expensive operation, and also too many writes can reduce the life of your SSD. So the operating system wants to be as efficient as possible, so they don't want to write too often to the SSD. So it wait for the buffer to get filled, and then only it gets flushed to the disk. But we have a problem here because the val file is very critical for Postgres, or the client, because the Postgres wants to issue a transaction commit to the user who performed the query, right? So like I said, Postgres doesn't lie. So if it has to say that, hey, I have successfully committed, then it has to be in the disk. It shouldn't be in the operating system cache or any other cache. It should be in the disk. So this is where something called fsync helps. So with fsync, Postgres actually tells the operating system to do an fsync operation. That means, hey, I don't want to trust your operating system cache or buffer or whatever it is, because it can be lost if something happens to your cache or your process. So please write these records directly into the disk and give me a confirmation. I will wait for that. Postgres will simply tell this instruction to the operating system. Then the operating system decides that, oh, this is important data, so I shouldn't mess up by keeping this in the memory, in the file system cache. So I'll perform a direct write operation into the disk. So the operating system will write the file onto the disk and then gives a confirmation back to Postgres that, hey, okay, I accepted your request. I actually performed the insertion into the physical disk. It's no longer in my cache or anywhere. It's in the disk. So you can trust. You can trust my word. So then the Postgres is happy, and then Postgres will tell the user that, hey, I have successfully committed that particular transaction. So it's now in the disk. So no matter what happens, it is always there in the disk when you restart the system next time. So this is how the val works. I hope now you got an idea about how transactions are made durable even in the case of system crashes. So I hope you like the video. Thanks for watching.